Alright, welcome back. For this lesson we have text problem 22-4. So at this time, as always, get out a blank piece of paper or a blank printout of this problem so you can follow along. Alright, first up, our read step. As we go through this, we see that we have two particles. One is a negative charge and the other has a positive charge. And they are separated by some distance, and here we are given the position along the x-axis. Alright, and so we are tasked to find the electric field between the two particles. So we have electric fields and we also have point-like particles. Now the reason we say that is that that'll come into play next lesson when we talk about surface charge distribution. So here we just have point particles and they behave much more simple compared to a uniform charge distribution. Alright, so let's get into our draw step. We're going to draw this out. Alright, so here's my drawing. Now it does say that they are attached to the x-axis, but to make the drawing look pretty I had them offset, but they are here and here at their respective positions on the x-axis. Alright, now do we have any assumptions to make? Oh, first we have to do our givens. Givens, we are given the charge on particle 1 and particle 2 as well as their positions. And I have the positions listed up here, so I'm just going to do the charges. Alright, so I have my charges given a little differently, but they are still equivalent. Instead of saying 2 times 10 to the negative 7, I wrote down 0.2 microcoulombs. Okay, so as we learned from our last video, be careful of your prefixes. So I put the prefixes in here to show the relationship between using exponential notation and using prefixes. So you can see the connection there. Now let's go into our assumptions. Alright, so we have to assume that we have a closed and isolated system. That means that we don't have any other sources of electric field in our system, and we don't have any sources of electric field outside of our system that are influencing our two particles. Okay, so that's what that closed and isolated system means. And let's get into our tasks. We only have one task, and that is to calculate the net electric field at the halfway point. Now notice that my electric field, or my net electric field, is dependent on the position of my charges. And so that's why I have the halfway point inside of parentheses here, because our electric field is inherently dependent on the distance between the charges influencing the system. Alright, so for the physics step, go ahead and pause the video and look at your PRC, look at your book, and write down the equations you think you might need for this problem. Alright, so we will need the electric field due to a point-like particle, and so that's what we have listed at the top. And notice that it is a vector quantity, and that vector information is here in our r-hat unit vector, which is the vector pointing from a point-like particle to the position in question, i.e. at this midway point, what direction is our electric field pointing due to this particle for E sub 1 and then this particle due to E sub 2. Alright, now we do have two electric fields, one from particle 1 and another electric field from particle 2. In order to find the net electric field, we have to add up our electric fields. And so that's what I have listed here. The net electric field is the sum of the electric fields in the system. And in this case, N is equal to 2 because we only have two particles. They are vector quantities, So what are we going to have to do in order to find the net electric field? We're going to have to break it into x and y components. Alright, so e sub 1x plus e sub 2x will give us our x component of the net electric field. We'll do the same thing for the y component. Alright, let's get into solving. Alright, so as we get into our solve step, I want you to pause the video again, and I want you to draw the vector arrows only along the x-axis for the electric field on particle 1, and then draw the arrows, the vector arrows for the electric field on particle 2. I'll give you a little hint. They should be either pointing at the particle or pointing away from the particle. Alright, see you in a second. Alright, so how'd you do? Well, let's take a look at this. For a negatively charged particle, the electric field is always pointing isotropically towards it. So here I have it just on the x-axis, but in reality it is pointing in every direction. Isotropically, that means every direction. And in this case, it is equal in every direction. That's, again, isotropic. For a positively charged particle, the electric field is always pointing away from the particle, isotropically. Now, we're only concerned about the x direction, and so that tells us that right here at our midway point, we have an electric field due to particle 2 pointing in the negative x direction, and the electric field due to particle 1 is also in the negative x direction. And let's make sure I annotate. This is Q1 and this is Q2. Alright, so let's get to work and actually calculating out the actual numerical value of the electric field at the midway point. Alright, before we can actually calculate the magnitude of the electric field at the midway point, we have to find out how far the midway point is from each of our charges. So that's what I have listed here. First, we have to look at the distance between our charges. It's 15 centimeters, and the distance from either charge to the midway point is just half of that, so 7.5 centimeters. Notice that our significant figures just drop down to 2. That will play into the solution in the end. So I want you all to pause the video, and I want you to calculate the electric field due to point 1 at the midway point. And this is just for particle 1. And remember, this is a vector. Alright, I will see you in a minute. Alright, so how'd you do? Well, let's take a look at it. We have first our base equation. Coulomb's constant times the charge times the distance from the point to from the particle to our midway point times our direction information. Now, remember when we were working with our drawing up here, we said that the electric field due to particle 1 is pointing in the negative x direction. Well, as far as unit vectors go, that's going to be the negative I hat direction. Alright, so that gives us our directionality. Now on the PRC, we don't have the absolute value of our charge here. We want the sign of our electric field, which gives us our direction in each component, to be based off of the particle and its position and not the charge on the particle itself. If we were instead asking for the electric field due to Q1, which is a negative charge, right here to the left of the particle, then the electric field would be pointing in the positive I hat direction. If we left the sign of the charge in there, then we'd have a problem because our direction information would have an inherent negative sign because of the charge. So always take the absolute value of the sign on your charge and allow the negative or positive aspect of the component of the electric field due to a particle to be based off of where you're measuring the electric field. All right? Okay, so that's the whole idea behind drawing out or using a sketch so that you can see what direction your vectors are pointing. All right, from there we put in our Coulomb's constant times our absolute value of the charge. Notice that I'm back into proper SI units, so not microcoulombs, but times 10 to the negative 7 coulombs. And I've also converted my 7.5 centimeters into meters. So I have times 10 to the negative 2 meters. And that all squared. And I get, as a result, 3.196 times 10 to the 5 newtons per coulomb in the negative I hat direction. Now, our charges on particle 1 and particle 2 are equal in magnitude, but opposite in charge. And as we look at the electric field halfway between the two of them, we already notice that they are both pointing in the negative I hat direction. So the electric field due to particle 1 at the midway point is going to be equal to, in magnitude and direction, to the electric field at the midway point due to particle 2. So I can write that out. E2 as a vector at the midway point is equal to the electric field due to particle 1 at the midway point. So as I add up the electric field due to both particles, oops, too many E's there. I need to add up the electric field due to particle 1 plus the electric field due to particle 2. And since E1 is equal to E2, I can say that it is just 2 times the electric field of the first one. And again, this is a simplification based off of where I'm measuring the electric field, and because we have two particles with the same magnitude of the charge. Alright, so once I do that, I take what I have right here and multiply it times 2. And so I get the net electric field is negative 6.4 times 10 to the 5th newtons per coulomb in the I hat direction. Two things to note. Notice how here I have a positive number but with a direction in the negative I hat direction. I can move that negative sign out in front. And that's what I did. Notice I only have two significant figures, and that is because the way I calculated the distance between or the distance from our particle to the midway point. And it's the nature of looking at the significant figures listed here in the distance between the particles. When I do adding or subtracting, I can only keep the level of accuracy of whichever value has the least certain accuracy. So 21.0, that means that my result can only go to one decimal place. And so when I divide that in half, again, I can only go to one decimal place because of my level of accuracy. Okay. Well, that concludes this problem. You can easily make this a more difficult problem by adding more than one particle or looking at the electric field at a place other than the midway point. And so you do end up with some differences between the electric field due to particle 1 and particle 2, and you would not get this same simplification. Well, we'll get a chance to do some more complicated problems later on in this block before the WPR. All right. Good luck with your physics, and see you next time.